Welcome to session 9. In this session, we will talk about how neural networks actually function. One important function of neural networks is in clustering. The clustering problem starts with recognizing that points close together in the input space have very similar y values or actual values. So if you have two such points within such a region, it is quite possible that the y values are the same and therefore could be easily determined. The question is, how can we detect and isolate such regions? Let's take a simple example with a 2D input space. In this case, we have x1 and x2 as inputs. We could have one cluster, and points within this cluster would have the same y value of 3.5. We could have a different cluster further away, and points within this cluster would have y values of 5.0. Similarly, could have other clusters. Here we have two more, 4.0 and 2.3. Let's review what a neuron actually does. It would take an input, x1 and x2, perform a dot product with its weights, and add the bias. And this part is called the linear combiner of the neuron. And this result would be saturated using some kind of function. I've chosen to use the hyperbolic tangent. The output is the predicted y, which in this case is simply the hyperbolic tangent function applied to the inner product. Let's visualize this with this diagram. The line where the inner product with the bias is 0 is called our decision boundary. The dotted white line is the decision boundary for the neuron N1. Points above the decision boundary have an inner product larger than 0, and points below have an inner product less than 0. Neuron N1 would be part of many neurons in the first layer. We have in this case 3 neurons, N1, N2, and N3 in the first layer. Each of these neurons would contribute a single decision boundary. So N1 could be this, N2s could be this, and N3s could be a different boundary. What we notice here is that N2's boundary bisects the region for 2.3. And this is not a good thing, because ideally we want each boundary to separate two different regions cleanly. How do we solve this? Well, in the second layer, let's focus on a neuron x1. Let's assume for the time being that we do not include as inputs into x1 the neuron n3, just to simplify the reasoning. So we have n1 and n2, and we'll just ignore n3 just for the time being. In the first quadrant, we have both n1 and n2 being bigger than 0. In the second, n1 bigger than 0 while n2 is less than 0, and similarly for the other regions. If you recall, the hyperbolic tangent saturates at both ends. On the right end, it saturates at positive 1. It has a middle linear zone, which we'll color in blue. And at the other end, it saturates at -1. Let's see how this can be drawn onto our clustering diagram. We'll color the linear region in blue and the saturation regions in red. In the first region, N1 and N2 are equal and they both saturate to 1. In the next region, N1 saturates positively because the dot product is bigger than 0, but N2 saturates at -1. And similarly, you get different relationships for different regions. We'll call the first region A, B, C, and D. So again, we're going to just focus on neuron x1 and ignore the effects of N3. So the inputs into x1 are just the neurons N1's output and N2's output. So the input space of x1 consists of just the outputs of N1 and the output of N2. Because we have used a hyperbolic tangent saturator, these outputs will be limited, of course, to -1 and 1, which is the unit square, shown in green here. Again, I've colored the linear region in blue. In practice, this linear region will be much fatter than shown here. I've made it skinny just for illustrative purposes. The corners of the square correspond to the regions A, B, C, and D, where both of these neurons saturate. Let's assume that the decision boundary for X1 is shown in yellow, like so. What we notice is a few things. The first is that the decision boundary of X1 never intersects the linear region of either N1 or N2. And this is really a consequence of the fact that tangent H saturates the outputs of N1 and N2. The second thing we observe is that the region X1 bigger than 0 completely encompasses the region A. So in our original input space, we will have N1 and N2's decision boundaries. We layer on again the linear regions of each, and this is region A. We know that X1's decision boundary includes A, but never touches the linear region of N1 or N2. And this is what it would look like. So what we see is that it is actually possible for X1 to join together segments of decision boundaries of N1 and N2. I'm not saying that this will always happen, just that it's possible. This in turn creates the possibility of nonlinear decision boundaries in the original input space by higher layers. Although each higher layer has a linear decision boundary, as this gets mapped down to lower and lower layers, the decision boundary becomes nonlinear. Lastly, we see that the topmost layer should separate the clusters so that the final LC layer can correctly label each cluster. Let's see this in action. Here again we have the diagram with the clusters and showing N1, N2, and N3 decision boundaries. If this is X1, and let's say this is X2, the clusters 2.3 and 5.0 are not separated. Can we solve this? And the answer is yes. The first step is to notice that each area can be labeled by the saturation values of N1, N2, and N3. So the 3.5 region is labeled by N1 equals to 1, N2 equals to 1, and N3 equals to 1, which we will call 1, 1, 1. Similarly, the other regions can all be labeled as well. These 6 points correspond to 6 points on a 3D cube. So the true input space of X1 is really a 3D cube because now we have the third neuron N3 as well. Previously, we made the choice to encompass just one point or one region where N1 and N2 were both 1 and N3 implicitly was also 1. Now we want to choose to encompass 3 points by the X1 decision boundary, and these 3 points are 1, 1, 1, minus 1, 1, and minus minus 1. Let's see how this would work. If we drew now the X1 decision boundary, it would appear as a crooked line in the original input space. You need to convince yourself that it is possible to draw a single plane in 3 dimensions that separates these points. On the left, X1 would be bigger than 0, and on the right, X1 would be less than 0. We draw now X2. In the upper region, X2 would be more than 0, and in the lower regions, X2 would be less than 0. So clearly, we have got 4 regions which are separated by different labels for X1 and X2. All the clusters, in other words, are uniquely labeled. And so the final LC layer only has to assign weights to correctly predict the Y values of each cluster. This final LC layer is responsible for the prediction. It has 3 weights, W1, W2, and the bias B. In order to make a correct prediction, all 4 of these equations have to be satisfied, 1 per cluster. Because there are 4 equations with 3 unknowns, at least one of them cannot be satisfied. This is one reason why we should not have too few neurons on the top layer. In the next section, I'd like to talk about the VC dimension and dimensional reduction. The Vapnik-Chernvonenkis dimension, or VC dimension, is simply the maximum number of binary clusters that you can separate using your neural network setup. Let's look at one example. Let's say we have a single neuron with 2D inputs like before. We can have one cluster and a second one because this is a binary clustering problem. With two clusters like this, we can easily draw a line to separate them. Similarly, with three clusters, we can still draw a line no matter how the clusters are configured. With four clusters, we cannot draw a decision boundary that separates them. So in this case, we say that the VC dimension is 3, because that would be the maximum number of binary clusters that we can separate. It might have occurred to you that if the three clusters were in a straight line or collinear, then of course we cannot separate these out. But we want to always disregard collinear or coplanar clusters. I'd like you to think about a few things. The first is to convince yourself that if we increase the number of dimensions to 3, we can separate 4 binary clusters as long as they are not coplanar. So, what is the VC dimension for one neuron with 3D inputs? And lastly, I'd like you to convince yourself that D plus 1 points in D dimensions can be completely separated using just one hyperplane. Let's move on. Let's say we have L data points with K binary clusters. Now, you'd have to have K much less than L in order to properly sample these clusters. If the VC dimension is less than K, it simply means that your model will be unable to learn the training data. On the other hand, if the VC dimension is much larger than K, then your model will overfit easily because any hyperplane would easily separate out these clusters. We can estimate the size of your VC dimension, and for feed-forward networks, it is on the order of the number of weights that you have. So if dim VC is the VC dimension, and W the number of weights in your neural network, we can use something called the big O notation, which I'll describe shortly. The big O notation simply means that the VC dimension is less than some lambda or some constant times the number of weights for large enough number of weights. We can estimate that the number of weights is the size of the first layer, N1, times D plus K N1, where D would be the dimension of the input space, and N1 again the size of the first layer. K is a small constant and it's usually less than 2 if your shrinking factor alpha is between half and 2/3. The big O notation does not mean that the VC dimension is equal to the figures in the brackets. It's simply telling us that the VC dimension doesn't exceed this asymptote, or more precisely, that the VC dimension is less than some constant times the figures in the brackets. This relationship gives us some further insights. The first is that the VC dimension increases as much as linearly with input dimension D. And second, we know that too high a VC dimension leads to easy overfitting. And this is called the curse of dimensionality. Here's something else you can think about. If we are not restricted to binary clusters, would we need more or fewer hyperplanes to separate K clusters? And secondly, can you estimate how much more or how much fewer hyperplanes we need in the worst case scenario? This brings us to dimensional reduction. One way is to use principal component analysis, or PCA. The other approach which we discussed in the labs are autoencoders. Autoencoders are very easy to use compared to PCA and also very good. Certainly they are much better than PCA, especially if your input points fall on complicated manifolds. Next, I'd like to discuss the effect of unimportant input. What these do is to increase the VC dimension, causing overfit to occur more easily, but also they can cause higher test errors. Let's see how. Let's say we have an input x1, and we have clusters, blue and red, which fall on different parts of x1. Clearly, we can separate them. Let's say we have an unimportant input x star. The clusters are now spread along dimensions x1 and x star, and this time the decision boundary is not easily drawn. It could be here, or for example it could be here. If we drew it here, superimposing the actual decision boundary, we can see clearly that this cluster and this one are both misclassified. So the effect of unimportant input is that they cause higher test errors, and that is why we should try to eliminate unimportant input as quickly as possible. A simple way of doing this is using input scaling. By using input scaling, you can help to reduce the VC dimension, and this reduces the chance of a bad decision boundary, and this in turn lowers the test loss. In summary, we have seen how higher layers act to glue together decision boundaries from lower layers. They don't necessarily create new decision boundaries. You need enough neurons, therefore, on bottom layers. Unimportant or large dimensional input spaces can adversely affect learning because the decision boundaries could be drawn incorrectly. You should use as many inputs as possible, but you should also use input scaling and an autoencoder to reduce the dimensions. I hope this session helps you to understand a little bit about how neural networks work.